or I start making sure facts. Yeah, that's true. That's very true. Okay, let me... Alright, so does everybody see the Discord? Understand? Bizzerno or Jacobson? My name is Bizzerno. I get it. You guys are just lively on chat. Problem is I can't watch everything. Alright.
You can't be a Mike Wazowski, sir, or whatever that girl's name is from Monsters Inc.
Okay.
A Diplexer.
So I wanted to get things straight here because you're going to see these items in the tisser before we start the schematics or Season Ds. Mainly they're boxes. So you can see a Diplexer. It says it's a passive device, implements frequency domain multiplexing. The bottom line is it's a three-way. And when you look at L and H ports, which are basically two frequency items with ferrite beads, and they've got some other filters in there to make them passive without any applicable electronic power to it. So you're going to see it. It's a three-way. That's all it is. It's a three-way. I don't know how the engineers came up with this, but the object is one of them is going to be your antenna. The other two is going to be a transmit line and a receive line, and that passive device knows which way to pass the transmit out the antenna and route the receive to the receive section without any interference. The other part of this story is you have a duplexer. This is also an electronic device, but it travels on a piece of wire. You're going to see this if you ever get that jumper between the baseband assembly and the RF assembly. Take a look at the plug. You will see a very small coax cable in it. That is where it's carrying the baseband and the IF back and forth between the RF section or RF assembly and the baseband assembly. So there you have it. I told you I would find it. Let's get on to the PowerPoint and talking about the signal flow. Now you have your slides and you have the electronic copy of the C's and D's, and what we're going to be looking at is the electronic copies of it. Now with this in mind, we're going to start on the baseband assembly. You can see down at the bottom of your transmit signal flow, this is the back of your baseband assembly. Now I think this particular one is, it says transmit baseband. That's the one you're going to look at. I think it's page 4. Hang on just a second.
You pulling out your printout, sir?
Yes. Okay. My paper copy.
Okay. Aaron Elder, it looks like your mic is stuck on.
Page 4. That's the one you're looking at.
Roger, sir.
Okay, so the first thing we're going to be looking at is the input. Now I want to point to this transmission traffic that's normally connected to your multiplexer. And the multiplexer is going to be bringing it in on whatever cable is that it uses to bring it on the back of the baseband assembly, and it comes in through this attenuator. Now on the front panel of the baseband assembly, there's an attenuator for the transmit baseband. It'll say XMTR on the bottom part of what I showed you earlier today. This attenuator is a little knob. It has 30 dB of attenuation on it. It has, actually it's two knobs. One is from 0 to 20. The other one is from 0 to 10 to give you a grand total of 30 dB of attenuation. What's it used for? Well, sometimes if you got your multiplexer really close to the baseband assembly, then it's probably going to be saturated in the front end of the baseband assembly, so you need this attenuator to bring it down to where it's approximately 3 volts peak to peak. Now, how do you know if it's 3 volts peak to peak? Well, on the meter on your baseband assembly is where you're going to view it. Next up, we're going to follow the bold lines going into what's called a baseband filter. This is a notch filter. The whole idea is to reject 8.5 megahertz for a reason. It's basically cleaning it up so there's nothing else at 8.5 megahertz. Then we come into the summing buffer amplifier. Now, back when we were teaching down to component level, this was basically a transistor, and I think it was a common base transistor, and they called it a unity of 1. And the idea behind this is so you can combine two different signals together to get one output to where it is a 1-for-1. In other words, if I give you 5 volts, it's going to give me 5 volts on the output without any degradation of the signal. And what is going to be on there are two different things. One is we're going to have pseudo NRZ, or we're going to have CDI, as well as order wire. Now, the order wire is going to be the 8.5 megahertz. So you saw back at that baseband filter, there was a reason behind that 8.5 megahertz being cleaned up. So you can put that 8.5 megahertz. Now listen to this, FM. It is FM. So when it comes out of that baseband or the summing buffer amplifier, we're going to trace it to something called a Diplexer. Wonder where you heard that one from. The idea behind this is we are going to let the order wire and mission traffic, better known as the pseudo NRZ and pseudo NRZ or CDI through, but we're going to block something called the 70 megahertz IF frequency from getting on that line back into, like the summing buffer amplifier and the baseband. So it's basically it's made up of filters to assist its back and forth flow of your baseband and your 70 megahertz. When we get out of that Diplexer, we are now on the back side of the baseband unit. We're going to take it, we're going to use either the 2-foot cable or the 150-foot cable, and we're going to connect it up to the RF assembly. And you can see the RF assembly off to the left there of our drawing. Again, look at all of these different items in how the transmit flow is going. You can see that we have the tech order, its references. So anything that I'm telling you is true. So we come out of the baseband assembly into the RF assembly, which is page 5 now. And you can see that the bold lines comes up and we get into the Diplexer. I wonder what that does. Wow. It's going to let the baseband in on one side and let the 70 megahertz go the other route. So therefore, we don't have a mix-up on either the transmit side or the receive side. Again, it's that little RF cable in that the 2-foot jumper or the 150-foot cable. When we go into our transmit synthesizer LRU, you'll notice it comes into a triangle. Most of the times that you see triangles, you can assume that they are amplifiers. Now, the idea behind this particular amplifier is to make sure that if I use a 2-foot, I'm okay. If I use the 150-foot, I got to compensate, because that's a lot of distance between the RF assembly and the baseband assembly, especially when you're dealing with digital. Remember, we were talking about signaling formats, the difference between neutral and polar. Remember, polar is a definite 10-volt difference versus neutral, which is 5 volts. So in this case, we're dealing with what? 3 volts peak to peak, because we're doing the attenuation. So when we get into here, that amplifier is going to amplify if need to be. You are also going to target this encoder. This is a transmit encoder, or the thumb wheels that we talked about this morning, and we're going to put it on a frequency that we need to transmit out. Now, with this in mind, I want everybody to understand that the standby operate switch I told you about is in the operate position right now. We haven't gone to standby, because we're not talking about loop back or anything else. So when we look at this, it is a BCD. It's binary coded decimal, ones and zeros. Back in the day, we used to teach these thumb wheels, and they were basically controlling transistors, and you either got a logic 1 or logic 0 out of there. We then go through a data switch. Now, that data switch is extremely important depending on what mode that you're in. In this case, we're in operate, we're transmitting. So if we were to go into standby, that data switch is going to do something different. We go into something called the VCO, that's voltage controlled oscillator, and what that's going to do, now please let me back up here for just a second here. This section right here, you'll notice the little letters right here that data switch goes into. It says PLL, that's phase lock loop. That means that when this comes up in here and gets modulated into an FM signal, we're going to take that frequency and make sure that it is on frequency with our phase lock loop. So not only does it tell you everything you need to know about what frequency you're on, but it also keeps you on frequency. You know, bye, in sync. Get it? No? Okay, never mind.
Yes, sir.
You guys are lively.
I get it.
Yeah, I know you do. So when you get up in here, you'll notice it says 7 gigahertz VCO, and then it has a ×2 multiplier. Now, the reason why we say 7 gigahertz, that's an approximate frequency. Now, what do you mean approximate frequency? I thought we're going from, baseband to the operating frequency. Remember back in the basic transmit signal, I'm talking about a basic radio here, you had baseband to IF, IF to RF, and RF amplification. So as you can see right in this general area, we're going from our baseband to IF. Now, the IF is anywhere between 7.2 to 7. I think it's 625. And the reason for that is, remember, our frequency range is from 14.4 to 15.25. That is half of those two numbers. So that's where we get that IF at. So we get, coming out of there, we go into a multiplier. Now this is a ×2 multiplier. It doesn't really do it. There's a reason behind when they say a ×2 multiplier. You see that little triangle that says multiplier underneath or above it? Well, that's really a transistor. The transistor is actually taking that frequency and amplifying it where it gets a harmonic. The first harmonic is the 7.625, and when you double that particular harmonic, you end up with your frequency range there of 14.4 to 15.25. Now on top of that, it also generates like the third and the fourth harmonic. Well, wait a minute, I don't want all those frequencies to be doing that.
Sir, I have a question.
Go right ahead.
Why don't you just tune the oscillator to 14 gigahertz in the first place?
Well, when you take that frequency and let's just say you went to 14.4, the problem is these amplifiers here and here, when you get to the FET, they produce a lot of noise. And what you have to do is you casually or generally bring it up to frequency in your transmit. And that goes for just about any radio that I have come in contact with, where they will do it in steps. And that's to prevent, number one, what's called the lower frequencies are easier to amplify than the higher frequencies. Now, if you take a look at 14.4 to 15.25, you're going to get a lot more noise on 15.25 versus 14.4. So that's what they do, is they bring it up in different stages. And this is solely for transmit. So that's the reason why they do that. And also, when you get the software-defined radios, it's a lot different because they're not having to deal with amplification at the front end. They can automatically go to it. It's really strange for the older radios. Older meaning, I want to say about 2010. When we started seeing software-defined radios, we're starting to see that around 2010, they changed the concepts of how they are doing what we're seeing here from an older standpoint. Now, it works basically saying they just do their amplification in stages after they've already got it to the RF frequency that they need. So there are, like I said, with technology, it leaps and bounds. So that's the reason why for the older radios. When I say older radios, probably anybody born around 1990? No? Is anybody older than, let's see, 90, 2000, 2010? Anybody older than 1978? That's how old you are? Wow, I graduated high school that year. Wow. It's a scary thought. Anyway, it just gives you an idea of the older radios. You're probably going to have to come across them one way or another. That's the nature of the beast.
So I'm still a little confused. Like, you say noise?
Mm-hmm.
What does that mean in terms of just like this? Like, what is that? I don't understand. Because like, if we're dealing with this stuff, isn't this like well above the range where we can hear it?
That
so
is
it wouldn't,
correct.
Like, really bother.
When I say noise, is amplifiers always generate noise in higher frequencies. And when I'm saying higher frequencies, we're talking the 14.4 to 15.25. So if I'm at 14.4, I could have almost went right straight to the main amplifier. And the noise factor when I transmit out would not harm my baseband signal. Whereas if I'm at 15.25, then I've got some major problems with that noise, and now my baseband signal, which has just got modulated on it, is going to have a problem on the distant end because the signal plus noise to noise ratio, the signal's not going to be that strong enough to defeat the noise. That's what it means.
Okay.
There's also things called a guide slope pad, which compensates for the amplification factors. It has everything to do with getting down to the nitty gritty of electronics. So that's what I can best hope that you would understand as far as noise is concerned. Noise being internal to the radio. Mainly amplifiers. That kind of give you an idea?
Yes, sir.
Okay. So we left off with the multiplier. The multiplier is going to generate a bunch of harmonics because that's what it does. When we get into the bandpass filter, in the tech order, it's going to tell you that we have approximately a 20, it was more like 200 gigahertz bandpass in here. 200 gigahertz? No, it's not 200. Gosh darn it. I think it's a 2 gig bandpass. I'd have to go back and look it up. But this bandpass filter is centered between 14.4 and 15.25. When I say centered, is it can go just a tad bit below 14.4 and a tad bit above 16.25. The object is I want to pass the frequency that I want and reject all others. That's what you're going to see. Now you're going to get into something called a Fet Power. That's field effect transistor. That's that bad boy right here. You have, it's going to amplify it. We're going to isolate it. Now, why in the world do we isolate it? Well, to keep any other signals that might get on that line to come back. Also, reflected power. That's what that isolator is. Oh, and by the way, right here is where the branch assembly starts. Remember, they're all passive devices. There you go. So from the isolator to the harmonic filter to the circulator to that standby switch to another circulator and out the antenna, that's all the branch assembly. So let me go on to more so you can get an idea. The VCO is going to frequency modulate. So you actually have two frequencies, the 8.5 who came in and got modulated again, and you have the baseband signals. Whole idea behind it, I need to get it into FM. That's the modulation type for the tisser. We have a ×2 multiplier, again, getting it to the RF frequency that we're going to use. The bandpass filter is basically rejecting everything else and letting our operating frequency go through. The Fet filter, this is where we're going to amplify it enough to where we get approximately 25 dBm or the 316 milliwatts. Here's the isolator. We're going to prevent any VSWR from getting back into the area where everything's being generated. Our harmonic filter, because we were at this FET, remember I told you back here you were going to generate harmonics? When you get into a FET, that's where a lot of amplification happens. And you're going to generate harmonics. This eliminates those harmonics. We go through a circulator. It's going to take us through the standby operate relay switch in operate mode. The idea is I'm not in standby. So I need to get out through this other circulator and go out the antenna. Now basically that circulator is nothing more than a duplexer. Remember I told you about duplexers earlier. And then out the antenna, out through the tisser. So that is basically our transmit path in how everything is utilized. Again, you can see this in the tech order. So as you can see, we haven't done anything different. We basically use the tech order to chalk everything up. So we're leaving off 4 and 5, and you'll notice that in the other side of the house we have 6 and 7. Again, the bold lines are telling us in receive. So in other words, we're swapping gears. We've transmitted out. Now we're going to receive. We have the RF assembly. It's where we're going to be going through. You can see the paragraphs that we're going through. And here's the receive path, the bold line. So we get the receive signal. The circulator is going to take our receive signal and pass it on to the receive section. This is the standby operate switch. Again, this is in the operate selector on the front panel of your baseband assembly. We're going to go through a pre-selector. Remember this morning when I was showing you the baseband assembly and there was the RF assembly, and I showed you where that little adjustment was. Remember now, there's 2 receive frequencies that you've got to put into the radio. The one that has a little tuning knob, that's the one where this pre-selector is. You're going to use that pre-selector in narrowing down the frequencies that you need to receive. It's going to reject all others. We're going to go through an isolator. Again, we have 2 devices, the pre-selector and the isolator, where the branch assembly is. No power whatsoever, just utilizing the passive devices. So you saw the transmit side where the branch assembly. This is the receive side for the branch assembly. We're going to go to something called a low noise amplifier, hence the triangle. We're going to amplify our signal because with a weak signal, you got to amplify it enough to where you got to mix it, which is the next part of this story. This is called an image reject mixer. Now, I'm not sure if you guys had anything to do with Dolan Hall. Is that a positive or negative?
Yes, sir.
Okay. Did they take you through what's called heterodyning?
Yes, sir.
Yes, sir.
Okay. So what do you get when you heterodyne? How do you get it to heterodyne?
You just combine 2 different frequencies.
Okay. And how many do you get
Yeah.
coming out?
You get 3.
One intermediate frequency, right?
I thought you get 3. You get like the upper band,
Yeah.
and then the
Okay, let me clear this up for you. What you guys were just talking about is modulation.
Oh.
Modulation, you're still taking it through a mixer, but because of the impedance on the output of that mixer, and depending on what mixer it is, you should get the sum, the difference, and the original. Okay, that's
Right.
for modulation. The audio that was coming in is at such a low frequency that when you put it on the output side of that mixer, it can't even see it because the impedance is just eliminates it. Now with receive, you got heterodyning. Now heterodyning works a little bit different than the modulation. This one we're going to take 2 originals like we did before, which was the audio and the RF, and mix it together to get our modulation. This one we're taking 2 RF signals that are pretty close to each other to get 4 out. 4. You're going to get the 2 originals, and then you're going to get the sum and the difference. So you have 4 frequencies total. Now, where did you get, like we did the modulation as well as the heterodyning, where's the first signal coming from? Anybody know?
The receive. Well, there's the receive, right? The receive signal you get.
Well, I'm asking to receive. So where's the first one we're going to get?
The receive signal.
Okay, so it's the frequency that you've dialed in. That's the one. Where's the other one?
The local oscillator.
That is correct, the local oscillator. Now, do you want the local oscillator the same frequency as you're receiving?
No.
No. In this case, we want it to produce a 70 megahertz coming out. So we're going to either do this oscillator that's back in through here. And this is where the receiving encoder comes into play. It goes through the RF synthesizer and then gives us pretty much the same thing that the transmit did. The deal is now it is going to mix with the signal to get us that 70 megahertz. So it's going to be 70 megahertz above the operating frequency or 70 megahertz below the operating frequency. So when we mixed it, go ahead.
Well, we need to know.
No, I'm just giving you an idea of what actually happens in the, yeah. Well, how are we going to get that 70 megahertz out? That's what I'm trying to explain here. So we get this mixer, we get the 4 frequencies. 2 originals, the sum and the difference. The difference being the 70 megahertz. We're going to run it through the preamp. Anytime that you mix, I have always seen after a mixer an amplifier. You can go back to the Prick 150 there and take a look at it and you'll see it too. So we're going to amplify it and we're going to bring it into another input amplifier because it's been so weak. We want to get it up to a level of amplification where noise again is not a factor. And then we're going to go through this bandpass filter. Now the bandpass filter is 70 megahertz. This one is centered on 70 megahertz. It can go 10 megahertz below or 10 megahertz above, which gives us a bandpass of 60 to 80 megahertz. Now what's it going to do? Well, that bottom line here, it's going to take out the sum and the 2 operating frequencies. So now I have 70 megahertz right after this bandpass filter. The AGC-IF filter is basically going to amplify the IF or bring it down depending on what it's doing. If you have an RSL on the front panel and it's above the green, yeah, your AGC's cranking and you need to figure out how to get that out of there. You probably have a problem with your AGC. But the object is I need to be in the green, and that's where that REGO comes into play because you want to have your output, in this case baseband, to be constant when it finally hits the multiplexer. So we have the amplification of our IF after we've mixed it, cleaned it, and we're going to go through the Diplexer. Now again, one way the Diplexer is passing our baseband and our order wire, the other hand we're passing that 70 megahertz. So this basically, that RF cable that you see in the jumper is a two-way street on one line. So you have transmit and receive. Do they interfere with each other? Everybody's going,
no.
No, they don't. Why?
Because the Diplexer.
Not really. Because one is traveling down the line at, let's say, what is 6.144 megabits per second, and the 8.5 megahertz order wire. Is 70 megahertz going to interfere with that? Nope. Too high. So that's how they can go back and forth on that line. And then once we get it out the rear of the RF assembly, it's going to go into the baseband assembly, which is page 7. Again, you can take a look at the tech order, to where it's at. We're going to come out of the RF assembly into the baseband assembly, page 7. We're going to go through a Diplexer. Again, this is going to let our 70 megahertz go through the receive section. It's going to keep the baseband and our order wire off the line. We're going to run it through a cable AGC. Remember I told you about the 2-foot and the 150 foot? Well, obviously if you're at 150 foot, you're probably going to have to amplify really a lot. If you only have the 2-foot, more than likely you're not going to have to amplify a lot. So that's what that cable AGC item does. Next up, we have a 2-box IF demodulator. The first one is it uses a discriminator. Now, with discriminators, we can always say that it's going to be FM. FM is a discriminator. So the idea here is you're going to recover your baseband as well as the 8.5 megahertz order wire. And the triangle next to it is an amplifier, because why? You just manipulated the signal. We're going to come through something called a low-pass filter. This is going to start passing most of our mission traffic and weeding out the 8.5 megahertz. Because of the low-pass filter does not 100% get the order wire out, we depend on this notch filter to get rid of it if it accidentally passes through. Not all filters are 100%, by the way. This one is pegged for 8.5 megahertz. We're going to go through a switch called FO/GM. This is on your baseband assembly. It is a knob. If it's fiber optics, oh gee, look, it says NRZ. Wonder why it doesn't say pseudo. Could be what I told you earlier this morning. Or GM, which is a CDI. We're going to go through an attenuator. With this one, however, it's only 0 through 10. And it's not going to require as much to attenuate to get that 3 volts peak to peak out. Again, you're going to have to look at your green meter or the meter to see if it's in the green to verify that it is 3 volts peak to peak. And then it's going to go out to your multiplexer. So this covers the transmit receive portion when your switch is in the operate position. In other words, you are transmitting out your baseband signal to the distant end and receiving from the distant end the baseband signal also. So now we're going to be looking at order wire. Order wire is our line. What does it mean by our line? It's maintenance. Us. Nobody else's. We can voice talk to everybody from the distant end if need to be. You're going to have a headset and a handset to talk to the distant end. So let's take a look at order wire. Again, this has to be in, to talk to the distant end, you have to be in operate. But to talk amongst each other, you don't need to. So we're going to take a look at this little area right here. I don't know if you can see my mouse. Everybody see my mouse? Couldn't hear you.
Yes, sir.
Yes.
Okay. All right. This says an order wire intercom. Okay. You can see that we have a speaker and also this connection right here. You can see that we have a connection for either, well, in this case, it would be your headset. I'm going to caution you again, do not put the headset on when you're going through the checking of your items, because you're going to come across what's called a test tone. And if you have that headset on, like I got my headphones on, it will blast you out. Protect your hearing when you're in electronics, gentlemen. Over a period of years, there is a lot of high-pitched squeals from electronic gear, and it will take out your upper end of hearing. So when you are dealing with these two, it's going to come through this bold line. You're going to see this transmitter subcarrier generator right here. You'll see it's at 8.5 megahertz. This is where you put your order wire. There's a discriminator in there to get it to FM. It's at 8.5 megahertz. It comes onto the summing buffer amplifier to combine with your baseband. There's that unity of 1 in the common base transistor. And again, We're going to come out, go through it, and then back down. Excuse me. If you are in receive, it's going to come out of your baseband signal, go into your Diplexer here as a 70 megahertz signal. The 70 megahertz is going to go through your cable AGC or IFD modulator. It will be two signals at this point. It could go through part of your low pass filter, but it's going to be taken out on that subcarrier notch. That's where everything ends for your 8.5 megahertz. However, you take a look at the bold line here. This is a discriminator. It's going to take out your 8.5 and bring it back in as audio. So you should be able to hear it. You know what's called side tone, and you should be able to voice. There's going to be another one, a handset on your base RF assembly, and the intercom is what you see, this little area right here. The intercom, you should be able to talk back and forth between your RF assembly and baseband assembly in standby loopback, which is a standby switch. This is what happens when you are in operate. So there you have it. Let's take a look at some of the other items that come up. Now you can see where I just went through the whole gambit of your intercom and order wire switch. This is in the order wire position. If you have this in intercom while trying to talk to the distant end, it's not going to work. Intercom means between your RF assembly and baseband assembly. Order wire means that you can still talk between your baseband assembly and RF assembly, but you can talk to the distant end. Remember, it's the maintenance line, not mission traffic. That's what order wire is. Again, the subcarrier generator is nothing more than a modulator getting us up to FM. The test tone oscillator, oh my gosh, that's the one that you got to worry about. If you have that headset on, forget it. Just put the headset and the handset on top of the RF and the baseband assembly. You'll do better. Won't blast your ears out. We also have a test tone detector on our front panel. There will be a test tone light, either, well, actually on both of them, your order wire and your, not order wire, your baseband and transmitter front panel. On that baseband assembly, there will be a T/T lamp. When you have that in the test tone, they should illuminate and you'll hear it. Now when we get into standby loopback, I've just described to you the voice side of the house, but also the RF frequency. How do we account for that? Well, remember that data switch right here? In operate, we use both encoders. Why? Because one of them is at least 200 megahertz away from the other, and that's so they don't have overlap. But when we do loopback, we got to figure out a way. If I do a transmission, how do I, get it demodulated back to me? Well, in this loopback, what happens is they put from this data switch, it's controlled by the standby operate switch. So when you put it in standby, this data switch takes the transmit encoder out. It puts the receive encoder in. So therefore, you're transmitting out what you should be receiving. And it goes through the same paths, except for one difference. Instead of going out the antenna, This standby operate relay switches it to what's called a dummy load because you don't want 316 milliwatts going back into the receiver. It could possibly smoke it. So they put the dummy load here. That's what that resistor is. And they take a portion of the signal and route it through the transmit line. That's how they're able to do a standby loopback. Kind of ingenious, the way I look at it. So you can see the key to the standby loopback is when it goes into standby, it's looping back on itself. That data switch puts the receive BCD in line so it can receive it. And of course, you got standby relay switches 1 and 2. They both control it. The idea behind it is to route that RF back into the receive section so you can demodulate it. So we've looked at purpose, operating characteristic, types of traffic, equipment flow, and signal flow. Any questions on that?
Yes, sir. I have one question.
Sure.
So at the start of the receive, why is the signal getting attenuated?
Receive path? Wait a minute.
The transmit path.
Okay.
I think it's the transmit. I don't. It's at the other one. I forgot the other diagram, and it's at the bottom right.
Am I on the right page that you were looking at?
No, sir. It's on page 4.
Ooh.
There's just the attenuate. Yeah, right there in the bottom right.
Bottom right. Oh, this attenuator. Oh, okay. All right. Multiplexers normally have and these are the ones that I've dealt with. Normally have a 5-volt peak to peak coming out. When you put it into the baseband assembly, it wants 3 volts peak to peak. So in other words, you're saturating it. And the reason why you don't want that to happen is you got to bring that signal down, and the attenuator is what does it.
Okay.
So the idea is to go from 5 volts peak to 3 volts peak to peak. And the attenuator is what brings it down.
Is there any reason why it's 3 volt peak to peak as opposed to 5?
That would be the design of the Tisser. Because the old FCC 100 had 5 volts peak to peak. Now, when you take a look at all of our signaling formats, what was all the neutral ones? What was their?
Was it 5?
Yeah, it was 5 volts. So if you got a multiplexer that's really close to your baseband assembly, let's just say you got a 10-foot cord, it's hitting that baseband assembly at 5 volts peak to peak. But let's say that you're in a deployment and your tent is, let's say, a couple hundred feet away from it. That's a long cord to do that. So by the time it gets to the front end of the baseband assembly, it doesn't have to bring it down. So it's basically a setup for how much you're going to send down the line and when it finally gets to the Tisser as to whether or not you need to bring it down. Now, newer models, when I say newer models, the P2P, from what I understand, they can accept the multiplexer because, it's a plug and play. That's what we've come down to now. So, but with this one, we need to bring it down depending on the multiplexer and where it's at. Anything else? Now you're going to get to see this really good for the next couple of days when you're in lab. Let's see about this one. 5 alpha. This is basic facts, state general principles associated with the controls and indicators of the Tisser, or better known as the... Geez, what happened here? Huh. Well, that's weird. Kind kind of cut off one of my sides here, and I can't figure out why that's the case. Let's see if I can bring it down. How about that? That a little bit better?
Yes, sir.
All right. So you're going to play with the tisser over the next couple days here. The whole idea is you will be pretty fluent on those controls and indicators. So remember the table that I showed you earlier? There you go. 4-1 and 4-2 controls and indicators. Everything you need to know about those controls and indicators is on that table. 4-1 being the RF assembly, baseband assembly being 4-2. Any questions? And 5 Bravo is your practicing and performing on the tisser. Any questions?
I have one, sir.
Sure.
If we did the student appraisal mass quiz, is there a way that we could get that graded prior to Wednesday? Or maybe even get the answer key later or something?
Well, we're not going to pass out the answer key, but I can go through it.
Okay, so if we submit it to you, say tonight or tomorrow, you could do it tomorrow evening or whatever?
Yeah, I could do it tomorrow evening, probably. When does everybody get back from lab tomorrow?
I think the last group is 11 o'clock.
Okay, so
Yeah.
I have a stream at 1 o'clock again for another class. So how about we make it for 3 o'clock tomorrow? In other words, what is that, 1500 to you guys?
Yeah.
Would that work for you?
It works for me.
Unless you guys want to take like an extra day, but that kind of runs us into doing a review as well as the appraisal, which is going to be a long day at that point. So you want to do it tomorrow, I would suggest that you get the appraisals done today. Is everybody in agreement?
Yeah, I personally. Yeah.
Any disagreements?
And I was going to suggest as an alternative, we can maybe like incorporate into the review we have on Wednesday.
He said if we do that, it'll be a long day, though. So I mean, I don't.
Well,
And I
when
was kind of me personally, I was wanting to have them separated as a redundant way of study.
I would like to have the answer to the appraisal and know that I'm right on those before Wednesday so we can study more. I agree with that.
Same.
It would also be nice for like a review day.
Right. So in other words, the way it's looking like, I got half of you that want to do it on Wednesday and half of you that want to do it tomorrow. Do I understand that correctly?
I'm fine with tomorrow, sir.
Shank, tomorrow?
Tomorrow works out good.
Sounds good to me.
That was Bizarno, right?
Yes, sir.
Prevos?
For me, sir.
So, okay, so here's how we're going to work it. Tomorrow at 1500, we'll go through the appraisals. Wednesday at 1300, we'll go through a review. Everybody
Sounds
clear?
good.
All right, so what I'm going to do is when I finally get done with this, I will post everything so that way you got a review, and then I will post what we're doing for the next couple days, and hopefully nothing runs over top of each other. And cross my
Yes, sir.
fingers.
Sounds good.
All right, well, we'll see you tomorrow at 1500, right? 1500?
Yes, sir.
Yes, sir.
I got to write this down or I'll forget it. So, class appraisals That's at 1500, and then Wednesday review at 1300. Now, more than likely, the review is probably going to be about an hour and a half. So come prepared, because I ask questions. All right. Any last things that you want to point out? Again, put on chat that, hey, you got some questions, please ask. I'm on till about 8 o'clock on Discord, and just off and on. I will probably answer it if you have any questions, because I do know that there is some tough questions on that appraisal. So if you're having problems trying to figure it out, I could probably give you some hints. If not, just give you the answer outright. All right, we'll see you tomorrow then. Everybody have a nice day.
Thank you, sir. You too.
Thanks, sir. You too.
You're welcome.